Okay. Okay. Good. Yeah, thank you for having me. My name is Sinikka Lennartz. I'm an assistant professor at the University of Oldenburg in Germany, currently visiting for 1 year at MIT in Mick Follow's lab. I'm going to present work that I did together with my colleagues David Keller, Andreas Oschlies, Bernd Blasius, and Thorsten Dittmar about global patterns of dissolved organic matter that emerge from microbial interactions. So most of this work is motivated by the so-called DOM paradox, which is that in every drop of seawater, we have thousands of different bacterial cells. And at the same time, we have thousands of different organic molecules that accumulate despite being surrounded by mostly carbon-limited bacteria. And if you add this up to the global ocean, this is a carbon reservoir of about 700 petagrams of carbon, which is more than the terrestrial and marine biomass combined. It's also a very old reservoir, so the mean age of this complex mixture of organic molecules is about 5,000 years. And that means it travels several times along the overturning circulation. And what will become especially important in this talk is it is also a very diverse mixture. So more than 100,000 different compounds have been identified on a molecular formula level, and there are probably a lot more. So the question here is, why does this dissolved organic matter accumulate while being surrounded by bacteria that, by not eating it, lock away a lot of carbon away from the atmosphere? And the common concept of that is that this is because of an intrinsic stability. So some molecules are just more labile than others, are therefore degraded much faster than others. So the typical concept that you see often is that the whole DOC pool is basically chopped up into different fractions, a labile one, a semi-refractory, semi-labile one, a refractory one. And this is also how we think about this, or how this is reflected in DOM models. So each of these pools gets then assigned a globally uniform degradation rate, but with it, it's then decaying while traveling along the overturning circulation. So we're looking mainly at net removal rates based on these somewhat prescribed reactivity classes. And what I think important in this context is also the heterotrophic microbial community is really the main degrader of the dissolved organic matter, but they are not really reflected in these models, in most of them. So there's really no feedback with the actual consumers. So therefore, we contrasted this concept of intrinsic stability with one that we call emerging stability. You can find in this perspectives article more details about it. Basically by saying each of these compounds here, of these DOC compounds, the green ones, is technically available to the microbial community. So there are no compounds that basically cannot be taken up at all. But by these interactions, the recalcitrance of the dissolved organic matter pool emerges at the systems level. So it's a property that the individual compounds do not have. They are all labile, but on the systems level, you still get a stable dissolved organic matter pool. And the mechanism behind that is because of this huge diversity of these compounds, this diverse mixture. These compounds can be taken up by a subsection of the microbial community. So they basically take up and therefore decrease the concentration of the individual compounds to very low concentrations, the subsistence concentration. But still, if you have this diverse mixture, this adds up to a large carbon pool as a controlling mechanism. Okay. By the end of this talk, I'm gonna get the switching done better. Okay. So does it make a difference to explicitly model the heterotrophic community, or does it not make a difference? So we will argue here that it does make a difference. When you look at the left side, this is the traditional way that dissolved organic carbon is represented in these models. So we have dissolved organic carbon change over time as some kind of input of DOC, usually tied to net primary production, and then decaying with a first order degradation rate. First order means it's just dependent on the amount of DOC in this respective pool. What this means for the DOC steady state concentration, which you can think of as the amount of DOC stored in the system, is that if you, for example, decrease the supply, for example, in the future, less primary production would lead to less dissolved organic carbon supply or production by phytoplankton, you will end up with less DOC stored in the system, which sounds intuitively right? But it's actually a difference to this emerging recalcitrance. Here, we're explicitly modeling a heterotrophic microbial community, and therefore this stabilizes the amount of DOC stored in the system. It becomes less sensitive towards the actual production term. And this is because if you say we decrease again the net primary production, less DOC production, you also decrease the biomass of the consumers, therefore decreasing the uptake rate, which then leads to the stabilizing of the system. So here we're making the degradation rate of dissolved organic carbon a second order reaction that depends on the DOC and the heterotrophic community. And therefore, kind of this model behavior switches. So what now controls the dissolved organic carbon stored in the ocean is really the properties of the heterotrophic microbial community. This is something that has not yet been that much taken into account. So let's see if this works. So how do we approach that? Our colleagues of mine have started to build a network model which takes into account these, or an interaction network between DOC compounds and bacteria. So let's see. Okay, so the video didn't work, but I put up a backup slide here. So we have different DOC compounds, different bacteria. It's just for visualization, we reduced the number, but we run this with a lot more. And then we have one or a few compounds that are externally supplied, which you see here in red, that get taken up by bacteria. And they diversify the carbon. This is something that we know from their experimental evidence. Release different compounds, get taken up by different bacteria, they diversify it again, and so we get this interaction network. And here, what is special about this model is that to kind of disentangle these processes of molecular properties versus concentration-driven uptake, we did not give them any traits so far. It is basically testing just the null hypothesis of purely concentration-driven uptake. So the only way these carbon compounds and the bacteria differ is by their randomly assigned position in the network, which we then run several times and then take the mean out of it. So this is work that was already published in 2019 by my colleague Andrea Menkes. She built this network model and basically could show that with these basic assumptions, you can already get to the mean concentration of dissolved organic carbon in the ocean and also the radiocarbon age. So this is really a mechanism that can explain how this carbon, which technically can be taken up so quickly by microbes, can still get to this age of several thousands of years. But we wanted to see whether we can take this mechanism or this model and also be able to reproduce the patterns that we observe of dissolved organic carbon in the ocean. So generally, we see a gradient with depth, so higher concentration at the surface, lower in the subsurface, and we see an accumulation in subtropical gyres. So using a mean field approach, we simplified this model so that we do not have this detailed network anymore, although the model still retains this behavior of this network. You can see on the right side. So this is just a sensitivity study towards different model parameters. The black one is the simplified version, and the gray one is the detailed network model. You can see we're still capturing the same dynamic, but here, and the mechanism behind that is still the same. We just need to kind of account for this diversity in the model with a specific model parameter once we're not resolving the network anymore. But then we added this network model towards in a biogeochemical ocean model, the University of Victoria Earth System model of intermediate complexity. So the added part is the microbial model for microbial DOC interactions. So still a DOC, still bacteria. The remineralization rate of the host model is actually the supply for the DOC taken up by bacteria. And then they release carbon during growth and during mortality. And of course, respiration is also considered. So when I just put this in, as I told you, into the model, this is what we get. We can, of course, explain the persistence as we've seen in the box model. It's basically just the R star concentration, but we cannot resolve the global pattern. So you get a rather uniform concentration of this organic carbon, which makes sense because we haven't given any of the bacteria any different traits. So they are just like performing the same everywhere all over the ocean. So the next step that we did was go through all of the model parameters and look for evidence in the literature or any environmental control on these parameters. So for example, temperature effect on the maximum growth rate or nutrient trade-off or effects on the bacterial growth efficiency and so on. And you don't need to necessarily look at the details here, but just to let you know that each of these environmental controls has a specific imprint on the DOC concentration. So we compared these analytical solutions to the largest standardized DOC, this organic carbon reference, or the largest database of these reference measurements to identify the one that we would then put in the global model. And what we found was explaining the observations best was adding a macronutrient co-limitation. We talked about limitations already in previous talks, but more than 20 different studies that performed these enrichment experiments showed that in large parts of the ocean, the heterotrophic community takes up more carbon if you add inorganic nutrients or inorganic and organic nutrients together. So what we did was basically reducing the DOC uptake rate when there are low macronutrient concentrations. You can think of this as implementing a trade-off line, and then the gray lines would be the individuals. But since we're just looking at the whole microbial community, we do not implement like specific traits of one strain, but really more like the community connection. And once we did that, we could explain a large part of the patterns that we observe in the surface, so the persistence and the global patterns. In the background, you see the DOC concentration as it's predicted by the model. And here, with this white background, this is the reference data in the same color code. So if you look here, we're capturing this transition with increase of the soft organic carbon coming from the Southern Ocean towards the equator with some, maybe I should show this as well here, the remote community, and the accumulation in the gyres as well. There in the upperling regions, there's a little bit of a larger model data mismatch. This is because the host model has a bias there on the macronutrient concentration. So we're kind of thinking it is a bit wrong, but for the right reasons in these regions. So what was surprising to me, however, was that when we think about macronutrient limitation, we mainly think about the surface ocean because that's where we have low nutrients. However, implementing this process also helped to reconcile the subsurface patterns. So we're capturing actually with just implementing this process 70% of the variance in this reference data set, which is more than 30,000 measurements. And I want you to pay especially attention to the Atlantic, because there you can see that up on deep water formation, we have this slow decline of the soft organic carbon concentration. And this is something that reproduces observations, and also these observations had been used to define the reactivity classes of these net removal rates in the first place. But here we're seeing the same pattern emerging without prescribing any systematic differences in the molecular composition or molecular properties. So we use this model to also look at how the DOC pool might evolve in a future scenario, now that we have kind of explicitly included the heterotrophic microbial community in a very, of course, in a still very simplified and very broad way. But just to see how this would look like. And not surprisingly, since we're kind of going towards lower concentrations of, in this case, phosphate in the surface ocean, we're building up the dissolved organic carbon pool because just the heterotrophic microbial community is limited by carbon in this case and does not take up that much carbon anymore. But if you look at the actual numbers, you can see that this is a rather weak feedback. So this will in no way kind of compensate any of the anthropogenic fluxes. However, the point that I want to make here is that we're kind of reversing the sign of the expected change of the dissolved organic carbon pool in the future. So in this traditional net removal rate approach, as I've shown, the steady state is most sensitive to the producer side of things. So how much dissolved organic carbon is produced by the phytoplankton, because the heterotrophic community is not really considered. So this would lead to less nutrients, less primary production, less DOC production, and then less dissolved organic carbon stored in the ocean. In this new approach, the steady state becomes much more sensitive towards the heterotrophic community. So we have less nutrients, therefore a lower DOC uptake, and therefore a more DOC storage in the ocean. So really, it's the sign of the expected change that is reversed. So this brings me to the take-home messages, so to say. Really, that considering the heterotrophic microbes in these models dynamically couples organic matter and production. And this has some implications on the evolution of the DOM pool. We can explain the persistence of the dissolved organic carbon, even if we only consider concentration-driven uptake. So if you're familiar with the DOM paradox, this would allude towards the dilution hypothesis or diversity hypothesis. And finally, it's really the heterotrophic microbial traits that govern the variable DOC storage in the ocean. And I think this means that we should look into this further, even in global modeling studies. And with this, I'm at the end of my talk. I thank you for your attention. Shamelessly using the opportunity to highlight that there's a PhD and a postdoc position in my lab, but I'm happy to take any questions.
Any questions? Can Anne, can you ask your question? Unmute yourself and ask your question.
Well, I was just clapping, but I do have a question. So you say that the very old DOM is an emergent property of the model. It's because of the network. I just find it hard to visualize, because if all the rates in the network are high, how do you ever get very old DOM? There must be some very slow rates in that network to get this very recalcitrant DOM. How does it work?
So it's a great question. So with the global model, we are not yet able to reproduce the age, or we actually cannot look at the age yet, because you would need these individual concentrations to look at the age, because it's internally cycled. So we cannot look at this at this point in the global model. We're working on this. But in the network model, you do get indeed small rates, because you have this huge diversity, and especially the compounds that are located further away from the entry point. So I've shown this network with this like kind of compound that is supplied, and then the carbon travels through the system. So those that are very far from this entry point, they receive very low concentrations of carbon. So they have kind of, since the uptake rate is depending on the concentration, it gets very low because the supply rate of carbon is so low at these compounds in the network, and they are the oldest ones.
Right. So essentially, you get a low supply of carbon there in that part of the network, and therefore also a small community of bacteria are utilizing that carbon. So it's basically a second order process. So that's why you have a small amount of substrate and a small amount of organisms using that substrate, and that together then makes the process very slow.
This is exactly the mechanism.
Right?
Yeah. Oh, sorry. Did you not hear me?
No, can you hear me?
Yeah. So this is exactly the mechanism, yes, as you described, because it's a second order process, low concentration of the individual compound, low concentration of the respective consumer community, and therefore
yeah. Thanks. Yeah, great. Very interesting.
Any other questions? There is one more online. Who's that?
Hi, it's Naomi.
Yes.
Hi, so this is Naomi Levine from at USC. Really exciting talk and some great results. I just had a question for you to hear your thoughts on. So the heterotrophic traits and putting into the models really exciting, and I'm so happy to see that. The relationship between phosphate and growth rate, and then having that result in better fit to observations. Obviously, phosphate in the real ocean is correlated to a lot of other things that could also be impacting DOM cycling, such as changes in phytoplankton composition. So I guess I'd love to hear your thoughts about whether you think it's the heterotrophic trait of more higher growth rate at higher phosphate, or whether there's other shifts that are kind of being compensated for by that model dynamic, like even shifts in between copiotrophic and oligotrophic bacteria, which would also follow the same relationship.
Right. That's a great question, because I think, so it doesn't even, I tried to say macronutrients because this model kind of has a stable ratio, so we cannot even differentiate between the different nutrients. So I think this is really a broad perspective from a global model that you could, I'm sure there are much more subtle details and different limitations, co-limitations, and other processes going on. So I think it would be like super interesting to go more into these details as well. So this was just kind of the proof of concept study, but yeah.
All right. Well, I just wanted to follow up on that question a little bit. So I'm not super into the DOM degradation controls, but it is my impression that there has been some warming experiments that have also seen increased turnover when you warm up a system. And so I was just wondering about, it seems to me that the relationship to nutrient versus temperature is super crucial for future predictions. And so I wonder about how confident are you in your model that you reject the temperature regulation versus the nutrient?
So temperature is actually a super interesting point, because there are two processes that we've found like a lot of evidence for based on incubation studies or experimental studies for how the temperature affects these traits. And basically a higher temperature would, if you just look at one strain, of course, increase the uptake rate of carbon. So this works in, I don't know if I had this in one of the slides. This works in one direction, but on the other hand, temperature also affects the bacterial growth efficiency. When you just look at the DOC, these effects kind of cancel out each other. So they are not yet included in this model, but I'm actually hoping that I can follow, especially on this temperature point, even more, because it might be that they just cancel out in the current ocean, but this might be having an impact when like temperature patterns change in the future. So I think there might be some more subtle traits that are not yet included here. And temperature is certainly one of the interesting ones that I hope we can look at in the future. This is a really good point.
All right, I think that's it. And thank you, Sinikka.